Bismillahirrahmanirrahim. Welcome back. This is Sanaullah Khaskeli. As in my previous video, I have discussed the very basic concept of carry look ahead adder and ripple carry adder. Now, in order to understand hardware implementation, we first need to understand the software approach and its simulation. Let's look at the block diagram of RCA. Since adders are the combinational circuits, so they have no input clock. So, in order to analyze the speed, we have to analyze them at very low frequency. We know that the Nexum 4S DDR board has a frequency of 100 MHz. On that frequency, it is almost impossible to analyze the very minute delay of this circuit. So for this reason, we use D flip-flops, D flip-flop 0, D flip-flop 1, D flip-flop 2 and D flip-flop 3 in order to slow down the operation. Basically, the purpose of slow downing this operation is to understand the very minute delay, which I have already discussed in my previous video, that every gate has a delay of say milliseconds or nanoseconds. So how can we observe that delay? For observing that delay, we have to slow down this operation. Like in video recording, if we want to check the very minute displacement, what we do, we slow down our speed. Video. So in this way, we will do the same here. As you know, this is the block diagram of 16-bit ripple carry adder, and as per my previous video, the generated carry of first module will be fed in the carry input of the next module. It will be fed in the carry in of the next module. Final carry out will not be generated until and unless all the previous carries of 4-bit adders are not generated. In this way, we add 4 flip-flops to slow down the speed, so as we can observe very minute delay, as I have already told you. Now let's consider, we apply 1 here, say 4 1 here, 4 1 here, 4 1 here and 4 1 here. So, and initially Cin is 0. So our answer will be 4 1 here, 4 1 here, 4 1 here and 4 1 here and 0 here. So when we apply Cin equal to 1, this Cin will be fed in this ripple carry, and this will be 4 0. After second clock cycle, this C out will transfer to this Cin of the next 4-bit ripple carry adder, and these 4 1 will become 4 0 like this. Similarly for this one and similarly for this one, and in final we will get 1. So this is the correct answer of our calculation. So to get this answer, we have to wait for say 4 milliseconds for each flip-flop. So in order to understand actual delay, we implement the hardware, this circuit on hardware, and calculate the time of each flip-flops in our next video. Now we are in this second part of our video, which is software environment of ripple carry adder. As I have already discussed in my block diagram, that this module is designed using structural modeling, or also called block diagram modeling. So in this module, basically we design different modules in order to design a final module. These modules will be called in one module like this. This is basically hierarchical modeling. In this video, we first design a 4-bit adder, full adder, just a full adder using XOR and AND gate, as I have already discussed in my first video. This full adder will be called in 4-bit adder using full adder. As it is instantiated here. Basically, we use D flip-flops in order to make it sequential, so as we can check the delay. Basically, there is no need of flip-flops for software modulation, software implementation, but we have to analyze the delay at a very minute level, at a very tiny level. That's why we use D flip-flop, which are triggered using clock edge. In D flip-flop, this is the code of D flip-flop. Basically, first C in will be fed in the D flip-flop. This D flip-flop will generate C out after first clock cycle, and that C in will be fed in the C in of first full adder. Then this full adder will generate a C out. This C out will fed in the second D flip-flop. This D flip-flop again generate a C out, which is Q, and that Q will be fed in the next full adder, likewise in all full adders. This 4-bit full adder will be called in 16-bit ripple carry adders 4 times, like these. This is instantiation, sorry, not call, but instantiation. So we are basically instantiating our module. Now this module will be called in top level module, and this top level module, with the help of test bench, we will simulate this top level module. So this is all about software implementation. Now we will analyze our simulation. So you see, in post-synthesize simulation, our ripple carry adder, it take almost 10.357 seconds to generate C out, while for some it takes 6.586 nanoseconds. Generate sum, not the actual sum, because actual sum will not be same as input, because we are also inserting a C in bit. So if you see, after running it for long times, this is still not the correct answer, but it almost take 106.6 nanoseconds to generate this output. Still this is not correct, still need more times. From this we conclude that this module is quite slow. So we will also understand its post-implementation time. There is a little bit difference between post-implementation and post-synthesis. So I am not going to do the post-implementation, but For your understanding, this is a post implementation. You see, we just bring them to radix like this. Okay, and for full view, so that from this to this, in this module you have so that there is no C out even after 40 nanoseconds, while in post synthesize output was generated after 9 nanoseconds. So this is what we call difference. Make it 2 nanosecond more. Still output is make it 2 milliseconds. Trigger. So basically this is the whole concept I'm discussing with you. Same will be done in CLA. Same process we will follow in CLA. This is the hardware implementation of Ripple Creator. In this module we are going to apply 16-bit, first 16-bit. Say a bit of 16-bit of a equal to 1, or in decimal equivalent 65535. So you are watching this, there is a continuous shift from one unit to next unit. Basically this is going to generate actual sum. This is not the actual sum after applying Cin, but it takes time to generate actual sum. We are almost there to generate Cout bit. Basically this was a 16-bit number, and we are looking for actual answer, how much time it takes to generate actual answer. So here we go for actual answer, which will be a 17-bit number, 1 bit of Cout and 16 zeros. So this was the whole concept of my calculation, my project from start to end. We are almost there.